Today we present our conference paper on the state space of fuzzy cognitive maps using shrinking functions, authored by Leonardo Concepción, Gonzalo Nápoles, Rafael Bello, and Koen Vanhoof. This study is devoted to understanding the foundations behind fuzzy cognitive maps, FCMs. Our main goals are to introduce several definitions and theorems that unveil the dynamic behavior of FCM-based models equipped with transfer F functions, to estimate bounds for the activation value of each neuron and analyzing the covering and proximity of feasible activation spaces, to prove the convergence of the state space of any FCM model equipped with transfer F functions, and to understand the poor performance of FCMs facing complex simulation problems. As an introduction, fuzzy cognitive maps are recurrent neural networks for modeling complex systems. Existing theoretical studies on FCMs are mainly devoted to convergence issues, commonly covering the existence and uniqueness of fixed points, while other results address the convergence of FCM models used in prediction and classification scenarios. Concerning the theoretical analysis of FCM's dynamics, we summarize our paper unveiling the dynamic behavior of fuzzy cognitive maps. First, we introduce several definitions and theorems that allow studying the dynamic behavior of FCMs equipped with monotonically increasing functions bounded into non-negative intervals. The strong version of our theorem proves that the state space of an FCM shrinks infinitely and converges to a so-called limit state space, which could be a fixed point attractor in some cases. This allows envisaging, to some extent, the FCM model's behavior before the inference stage. As a second contribution, we explore the covering and proximity of feasible activation spaces, which help explain why FCMs sometimes perform poorly when solving complex prediction problems. In other words, we show why we should not expect impressive prediction rates when the model has low covering values, as the FCM feasible state space is small. In order to introduce it to shrink functions and state space estimation, we define F as the set of all monotonically increasing functions bounded into non-negative intervals. Also, let F sub I belonging to F be the transfer function used in the activation process of neuron C sub I in the FCM. From now on, we refer to an F function as any function belonging to F. H sub W and H sub T are functions that take an FCM-based model M and a feasible state space at some iteration and return another feasible state space at the next iteration. The difference between both functions is that H sub W uses the weight matrix of M and H sub T uses the FCM's topology only. Based upon estimated bounds for the successive activation values and from the monotonically increasing property of F sub I belonging to F, we assert that, over the same FCM, these two shrink functions transform feasible state spaces into state spaces which are also feasible. To show that FCMs are not completely unpredictable, we propose two theorems as the pillars of our state space estimation: the weak shrinking state space and the strong shrinking state space. The former asserts that the state spaces shrink from one iteration to the next one, although the equality might hold for two consecutive state spaces. So, the state spaces may not shrink forever. The latter theorem only varies in the sense that transfer functions are now bounded into open intervals. This means that the state space bounds are never reachable, and hence the state spaces will shrink forever and they will have a limit. Such a limit is called the limited state space of M, and it is defined as the mathematical limit of the state spaces when the number of iterations tends to infinity. It can be iteratively calculated using either shrink function h sub t or h sub w. The limit state space often contains a single point. Covering and proximity are two evaluation measures that help understand the properties of FCM-based systems. The covering quantifies the proportion of the induced activation space that is reachable by the neuron's activation values, and the proximity measures the mean relative distance of neurons' activation values to the feasible activation spaces. The results confirm that better predictions for FCM's behavior arise working with stable maps and their weight sets. Small covering values are evidence of the reduced representativeness of induced activation spaces, but sometimes we desire high covering values to represent the most diverse sets of outputs. As illustrated, such measures have a straightforward connection with the strong version of the theorem. More importantly, they help explain why FCMs sometimes perform poorly when applied to prediction problems that demand high accuracy. The simulations reported more valuable results in the presence of stable FCM models and when the knowledge comprising to the weight set is available. This scenario has proven useful to predict the FCM's behavior, for example, fixed point attractors, by means of covering and proximity values. This allows envisaging to some extent the FCM model's behavior before the inference stage. Figure number 1 shows the distribution of covering values for stable FCMs using the h sub w shrink function. It reveals that 121 FCMs have small covering values between 0 and 0.1. Thus, we can estimate small feasible state spaces to which these activation values belong to. On the other hand, the figure 2 shows the distribution of proximity values for stable FCMs using the h sub w shrink function. According to this, nearly half of the proximity values are exactly 0, so almost surely 90 FCMs converge to a fixed point attractor, regardless of their initial stimulus vector. Summarizing, in our work we have introduced a theoretical formalism consisting of definitions and theorems to unveil the dynamical behavior of FCMs equipped with transfer F functions from the perspective of their state spaces. The strong version of the theorem enunciated in this paper ensures that the feasible state space of the target FCMs shrinks infinitely, yet the system converges to its limit state space. As shown in the experiments, approximating an FCM's limit state space is useful to predict fixed point attractors. Likewise, we illustrated that the covering of feasible activation spaces is often poor and irregular for FCMs with reduced network topologies. As a future research, this knowledge could be injected into the learning procedure in order to improve networks' performance. Thank you very much.